Hello everyone, this is Jerome Villapando and we are Group 55 and we present to you our FYDP called the Table UV and this is our final demo video. 2020 and 2021 are becoming pivotal years in modern history, and not just because of all the negative events, but because these years have brought to light a problem that has been occurring pre-COVID-19. Before the start of COVID in the US, more than 2.8 million people were afflicted with an antibiotic-resistant infection, not including prominent viruses such as HIV and influenza. Unfortunately, as a result, these infections had led to the deaths of 35,000. In our FYDP group, we have a vision to significantly reduce disease transmission by designing an accessible and economical device for the general public. Although masks and a frequent hand wash habit can effectively reduce the risk of infection, common surfaces can be a major cause of disease transmission. According to Public Health Ontario and many other publications, bacteria and viruses can remain on the surface for more than 2 hours and can even stay for days depending on the surface and environment conditions. Because of this, we want to target reducing transmissions through services, specifically targeting objects in public areas that are meant to be shared with numerous people. The current solution is disinfection by manual labor, which somewhat defeats the purpose of the action. Plus, the effectiveness of the disinfection is not controlled nor measured. Some autonomous solutions cost over $100,000, which are often bought solely by medical institutions that have the budget to stomach that cost. We aim for our device to fill the gap in that market by designing an autonomous and affordable solution to disinfect surfaces.
First constraint, we have that the robot must be able to disinfect at least one table of 1.2 by 0.7 meters in one charge. Although exact measurements were not taken, the robot could run multiple times around the table with all sensors fully functional during testing. With that in mind, it is reasonable to assume that the robot will be able to disinfect the whole surface of a 1.2 by 0.7 meter table in one charge. On to the second constraint, we have that the robot must be able to operate safely on the tabletop without knocking off objects. This criteria was met using the frontal collision sensors and the TOF distance sensors. The TOFs were able to detect low-profile objects such as forks and knives, as well as more high-profile objects such as bottles and apples. So a choreographed action is initiated by the robot when it detects an object within a certain threshold, rotating itself until the object is no longer seen. Additionally, in the case that the TOFs malfunction, the frontal collision sensors are activated through touch. So the third constraint is that the robot must be able to stay on top of the tabletop without exceeding its boundary. This criteria was met using the bottom-facing IR sensors that are triggered when the sensors detect the edge of the table. Similarly to when an object is detected using the TOF sensors, the robot initiates a predefined set of motion that backs off from the edge and starts moving at a different angle until the edge is no longer seen. And this allows the robot to successfully maneuver around the table without falling off the edge, covering more of the tabletop surface.
Constraint 4. The robot must be able to support a minimum load of 1 kilogram, including the robot's weight. This constraint was put in place so that this robot could also be used in other applications where it was necessary to use the robot surface as a holder for objects, such as utensils in a restaurant setting. Since it was decided that the robot will be using two-wheel drive, additional support is needed to keep it balanced. 2 ball rollers were implemented so that there are now 4 points of contact with the ground, allowing for more additional support. The robot weighs about 600 grams and can support an additional load about equal to its weight. Constraint 5. The cost of production must be cheap enough to be considered as a viable product for restaurants, libraries, and other public spaces. ideally costing less than $300 Canadian. Unfortunately, we were not able to meet the intended cost of $300. The main reason is that the electrical components ended up costing a lot more than expected. In particular, we had decided to over-engineer and choose the most powerful compact UV LEDs available to us just in case. Each LED costed around $10, and the robot contains 12 of them. Since we did not know how intense we needed the LEDs to be to achieve the disinfection needed, we used the best LEDs to be safe. Also keep in mind that since we only ordered the components in small batches, the unit prices for most of the components are not optimized, and some items can cost as little as pennies if we ordered in larger amounts. The use of off-the-shelf components such as the IMU and cables were also very expensive, which can be improved by designing our own IMU circuitry and FPC cables. Constraint 6. The robot must pose minimum risk to nearby people, such as UV exposure. Mechanically, the layout of the UV lights are designed to minimize UV leakage through the table reflections. The robot is elevated within 3 mm from table surfaces to increase the intensity of focus sanitization. We have a supervisor node and firmware to ensure the safe operation of the robot. As you can see, the UV is turned off whenever the robot is lifted or at the edge. This is done by checking the status of the IR sensors at the bottom of the chassis, or the IMU orientation readings. When these conditions are met, the robot goes into an emergency stop state that powers the UV off in hardware by toggling a pin connected to the circuit, in which disables its operation. In addition, we have an emergency power shut-off button that kills the power to the entire robot. Constraint 7. The robot must be able to sanitize up to 99% of common bacteria and viruses. In 4A, our group was in contact with chemical engineering professors Professor O'Coin and Professor Anderson about perhaps collaborating on verifying our UV LED implementation. They helped us gather white papers to get a grasp of what UV LED specifications we needed to achieve the 99% effectiveness. With this information, we designed the UV circuit accordingly. Unfortunately, due to lockdowns and the pandemic, we were unable to verify our configuration in their labs. Instead, we decided to over-engineer and design for higher drive strength and made the UV drive specs controllable through firmware. This allowed us to be flexible in the off chance we were allowed to properly test the UV effectiveness. Again, sadly, this was not the case, and this constraint was never fully verified.
Criteria 1. The robot must be small enough such that it does not occupy the tabletop space, ideally a palm size within 1,000 centimeter cubic. In order to achieve a super compact robot in a low profile format, everything has to be designed from ground up. In mechanical design, everything is designed with the unibody mechanical design with the 3D printing technology. So everything is efficiently printed and designed. Electrical-wise, all custom PCBs were cautiously designed and layouted with 90% space utilization, so they can fit in the tiny spaces compactly, as you can see in the image. As a result, the robot is 100 mm in diameter, 127 mm in height, so about 997.46 centimeter cubic. So it is within the spec of 1,000 centimeter cubic. For the criteria 2, the robot must be able to cover a wide area of the tabletop surface. As you may see in the clip, there are 14 UV LEDs, and it covers 90% of the area traversed. The LED is elevated 3 mm above the ground so that it can ensure the performance needed for 99% disinfection rate at the robot speed of 3 cm per second.
The third criteria is that the robot must be adaptable for it to be used in various environments. Although the robot is designed for tables, we have tested it on various surfaces such as the kitchen, floor, and the sofa, and the robot performed well. This is shown in the video on the right, where we have conducted tests on different surfaces and we can see that robot is moving and performing as intended. We have originally intended to test on tables in different environments, such as the library and restaurants for different applications, but unfortunately, due to pandemic, we could not perform these tests at those locations. However, as the robot is performing well on the tabletop, we expect the robots to perform in different environments as well. The fourth criteria is the production cost of the robot must be minimized. Although the overall cost constraint was not met, the team performed design optimization to reduce the cost as much as possible. This is done so by limiting the usage of off-the-shelf components, designing components from scratch as much as possible. For example, all of the PCB boards designed were kept under 2-layer board, which reduced the PCB cost by a factor of 10. Additionally, the team have limited the number of sensors on a robot by performing optimization on sensor placements to minimize the number of sensors and thus reducing the cost. The fifth criteria is that the robot must clean a standard table within 30 minutes. We define a standard table for our table of 4, in which the height is 1.2 meter and the width is 0.7 meter. We designed the robot based on a set of equations to find the parameters such that the robot is capable to clean the table within 5 minutes with 90% effectiveness on average viruses. As we can see from the video, it only takes 30 seconds for the robot to clean from one edge to another, in which the distance is 1.2 meter. Since the robot diameter in the UV LED coverage is 10 cm, for the robot to clean the table with 0.7 meter width, it needs to run 7 times, which only takes about 3.5 minutes, and therefore is much smaller than the defined 30 minutes. That is the end of our final demo video. I hope you guys enjoy it. Thank you.